This video is about PWM, Pulse Width Modulation. You already know that microcontrollers can output a 0 volt or a 5 volts. And you also know that analog voltages can be 0 volts and 5 volts and anywhere in between. PWM is the microcontroller's way of only needing to use 0 volts and 5 volts to be able to create any voltages between 0 volts and 5 volts, just like analog voltages. There are many uses for PWM with microcontrollers. These include, but are not limited to, sound, output, controlling motors, maybe dimming of LEDs, or just creating some approximated analog waveforms. Let's use this motor as an example of why we would need PWM output with our microcontrollers. You may already know that if you apply a voltage to a motor, then you'll make the motor spin. If you connected this to a microcontroller and you're only able to give it either 0 volts or 5 volts, it would either stop or go at its 5 volt speed. That doesn't really give you much flexibility. You may want the motor to run at different speeds, and you also may want it to run in different directions, clockwise or counterclockwise. So let's see what a motor does when we apply 1.5 volts to it. I'm going to put a paper clip on it so I can see the spinning of the motor and of the direction. So I'm taking the positive and putting it to the red lead, and the negative, and the black to the negative. You can see that it's turning in a clockwise direction. Now if we turn the battery around and have the negative pole on the red and the positive pole on the black, it turns in the counterclockwise direction. So what if we applied 9 volts to this motor? We're probably going to see that this motor is going to run at a much faster rate. And as we see, it does. The paperclip is causing a lot of out of balance, so that's why it was jumping around a lot. Let me do it without it. And you can see it's moving quite fast. Let's put the other battery, and we'll be able to hear the difference. You can barely hear it now. Let's go one step further and create a circuit that provides any voltages between 0 and whatever battery we'll be using, either the 9 volt or the 1.2. And we're going to connect it to a potentiometer so we can adjust the voltage going to the motor, and we'll see exactly what can be done with analog voltages and controlling a motor. I'm going to use a small breadboard and a potentiometer, as we did in the previous videos. I'm going to use one of these handy connectors for the 9 volt battery. And you want to try not to allow the two ends to touch, because that would be shorting the battery. And I'll put the negative on one of the outer leads of the potentiometer, and the other pole to the other outer lead of the potentiometer. And what we'll get is a voltage divider constantly being changed as we turn the potentiometer, going from 0 volts to 9 volts. Now I'll plug the two leads of the motor. I'm going to go ahead and just put the black to the black side, this outer lead of the potentiometer. Then I'll take the red one and I'll put it in the middle lead of the potentiometer. Okay, so when we turn the potentiometer, I have it all the way pulled back. If you turn the potentiometer, the motor should start turning. See if I can get it all into the camera here. You can see as I turn it, I'm getting relatively low RPM. Then I can start turning it up, and you can see that the motor will start to increase the speed until it gets to its 9 volts level. The same thing can be shown with an LED. The LED is actually going through another resistor it is connected to the middle pin of the potentiometer, and then it's connected with a resistor to the outside lead. And as we turn up the potentiometer, you'll start to see it get brighter and brighter. And then as we turn it down, it starts to dim. And with PWM, we can do the same thing with the microcontroller. And the microcontroller does this by pulsing its 5 volts very, very fast. So now we know why we would want to use PWM. Let's see how we can make PWM work. And with PWM, you have the pulse, and you have the pulse would be, if it was 0 volts, then it goes up to 5 volts, it goes down to 0 volts, and then the 5 volts again goes back down to 0 volts. These are the pulses. And you also have the period. And this is the period of time between the pulses. And the period happens where you have starting from the 0, and then you have the pulse, and then it goes back down to 0. And this is the period of time where the pulse happens. And this period is usually constant. The period of time is generally the same throughout the entire PWM sequence. The smaller the period, the higher resolution you're going to have with the voltage and trying to match a specific analog voltage. And I'll get more into that a little bit later. And you also have phase correct PWM, which is really just taking the period, which is here, and you're shifting the period so the pulse happens in the middle. As an example, let's just take the same pulses that we have. And the pulses would happen in the middle of the periods. The periods are still constant. You have the period here, and you have another period here, and you have another period here. These are the periods of time, which is only a constant number, and you would have the pulse happening between those periods. The pulse looks the same, it's just where it is happening within that period. And that is the only difference between a standard PWM and phase correct PWM. Phase correct just sounds like a very complicated term, but it really isn't when you actually see what it's doing. Now there's another term called duty cycle. And that only refers to the size of the pulse, how long the pulse is happening. You can have the pulse that we have a period. So the period is a particular period of time. And we can turn on the pulse. Well, let's start at 0 like we're supposed to here. So the pulse hasn't started yet, and then right in the sort of the middle of this period we'll have the pulse starting, and we'll go across, and we'll keep the pulse on until the period of time stops. And then it'll start all over again, and it'll come up to the middle of the second period, go across, and then come back down. And this would be a 50% duty cycle, because it's happening right in the middle of the period. And if we're talking about 5 volt to the top and 0 volt to the bottom, this pulse between this period would equal 2.5 volts. Let's say that we have a very thin pulse. Let's say our period is between these two lines, and our pulse doesn't happen until the very end, and then we have a little sliver of a pulse, and it does the same thing to the next period. And let's say this is a 20% duty cycle. This was 50%, and this is 20% duty cycle, because there's only 20% of a pulse here, or 1/5. And we already know what 1/5 is. That's 1/5 of 5 volts would be 1 volt. And if we had a 100% duty cycle between this period, essentially you'll have the period constantly on. It would constantly be 5 volts all the way through. So 100% of 5 volts is 5 volts. Now we have a couple of options working with PWM. When we're working with servos, if you wanted to feed a servo PWM, we could just give it to the servo just like this with these pulses, and it works perfectly fine just getting pulses. But maybe some other more analog devices might not really appreciate pulses, but a nice straight line of voltage. We've already learned in the converting AC to DC that we can take these pulses and we can produce a nice stream of voltage using capacitors. In the PWM, if you have a pulse like this, the first time the capacitor gets a charge, it's going to take the charge, it's going to take the voltage, and it's going to keep the voltage, and then when it sees no more voltage, it's going to start ramping down. But it won't go all the way down to 0. It'll catch the next wave of pulses, and it'll probably just come up a little bit and go back down. Come up a little bit and come back down. And it'll most likely be flat between where the pulse is, the length of the pulse. So you can start to see that there's now a line. Just by adding capacitors, you can create an actual analog voltage out of the pulse width modulated signal. So if we had a pulse width like this, with very little pulse, that would equal, let's just say this is a 0 volts and this is 5 volts. You'll have a line, if you had capacitors, you'd just have a line down here of voltage. If you had a pulse width modulation, a large one, with a lot of pulse on the top, and that would equal 0, 5 volts. That would equal more of a 5 volt or close to a 5 volt voltage. And with the microcontroller, if you modify this pulse width modulation using a loop or something else, you can actually create an analog voltage of whatever you want. Specifically, you can see how an analog waveform is created. Let's take a closer look in detail and see how a PWM output could create an actual waveform. Let's take some arbitrary waveform, and it doesn't really have to make sense. We're gonna say this is 0 volts, and up here is 5 volts. And in this waveform, to create the voltages that we need to match the waveform, we would have the periods, just like we would in the PWM. This would be one period, and all these periods would be the same, would be constant. It would be the same time frames, and we would have to sort of plot the voltages and determine the duty cycles for each one of these. So let's figure out these duty cycles. This would be 0%. This would be 100%. And let's say this is 25%. And this is 75%. So we can see this is kind of between the 25 and 50. So this would be around 37, 38%. So we can just put an arrow 38%. And at this period, we would have somewhere between 50% and 75%. Let's say this is 60 because it's closer to the 50. So that would be 60%. So the first period is 0, then we jump to 38%, then we go to 60%. And then the next period, we're almost at 75%. So we would say maybe 72%, let's say. And we would keep going until the actual waveform is created. And this would be data points that we would output in PWM with the microcontroller. But we can also, if it's a specific, this would be maybe some kind of frequency that would be maybe a sound frequency, and this would be a waveform that creates a specific type of sound. But it could be a waveform that is constant. Maybe it's a sine wave, maybe it's a triangular wave, and you can create any kind of waveform with a microcontroller, and it would be an approximated analog. And when I say approximated, you can imagine that the capacitor is going to charge up, and then it's going to sort of level out and then charge up again. So it's going to be a bumpy waveform, and it's going to go down here and then just keep falling to this point. So depending on if it's rising or falling, you'd have some bumps in here. If you didn't use a capacitor, you would essentially have just stair steps. So it would look something like this. So the use of capacitors is really trying to smooth out the curve, and it's really sort of interpolating the curve a little bit to a certain extent. With servos, we only need to have a period of a specific time period, and the pulse is going to be between, the period is actually going to be 20 milliseconds, and the pulse is going to be between 2 milliseconds and 1 millisecond. According to the servo manufacturer in the datasheet, it actually says the millisecond pulse has to be between 0.9 milliseconds, let's put 0.9, to 2.1 milliseconds. The 0.9 milliseconds will take it from maybe like this location, and then the 2.1 milliseconds would be in this location. And right in between the two numbers, the 0.9 and 2.1, you'll have the horn centered. So the pulse would be, let's say this is the ending of the pulse, and this would be maybe 0.9 milliseconds, and this would be 2.1 milliseconds. So we can have the width, the pulse width, vary from this point to turn the servo. We're not going to get nearly as much as 100%. We're just going to stay at this point. If we try to go over this, then you're going to be pushing the servo to past its maximum limits, which can damage the servo. So how do we create an actual PWM using the microcontroller? In the microcontroller, we're going to go back to timing. We've already created a PWM in one of our first tutorials, and that was the LED blinking. We had the microcontroller blink the LED. It was going on, and then we would turn it off. We would do this to a pin in the microcontroller, on and then off. And every time it got to one of these peaks, the LED would be on. And every time it was on the 0 volts, the LED would be off. And we passively created a PWM without even knowing it. We were just turning on a pin and turning off a pin, and this by definition is PWM, but it's a really slow pulse width modulation. If we want to create real PWM, we need to speed this up. So what we're going to do is use the timer in the microcontroller, and the timer counts up to whatever. The 8-bit timer will count up to from 0 to 255. So I'm going to draw that. Let's say this is time going in this direction, and this is the count in this direction. This would be 255, and this would be count of 0. So in time, the microcontroller is going to be counting up, and then when it gets to 255, there's just a little counter in the microcontroller going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to 255. It gets to 255, and then it goes back to 0, and it does it all over again. And this is called the overflow with the 8-bit timer. It goes back down to 0, and it counts up, and then it goes back down to 0. And if we wanted to use the 8-bit timer, this would essentially become our period. And our period has only a few, in the 8-bit timer, it only has a few variations because it always overflows at 255. We can create prescalers to slow this down. If we have no prescaler, this is counting with the clock, internal clock in the microcontroller. Right now, by default, the microcontroller has a 1 megahertz, or it is counting from 0 to 1 million within 1 second. Hertz means second. Whenever you have a megahertz, that's 1 million, and then which is mega, and hertz means 1 second, so it counts 1 million times within 1 second. If we remember back here, we have 20 milliseconds. The servo datasheet also calls this 50 hertz. So let's pretend this is 1 second. From here to here is 1 second. And if we divide this line into 50 parts, little tiny lines going to 50. If we measured between each part, let's zoom in on this little part here, this would be 20 milliseconds. And that's because 50 hertz, 1 divided by 50 hertz is equal to 0.02. And this number represents 2 milliseconds. Because if you just had 1 here, that would be 1 second, or 1 hertz. 1 over 1. If you had 1 hertz here and 1 on the top, you'd have essentially 1 second. So if you have 50 hertz, you're dividing 1 over 50, you're getting the space between each part of the division. This digit in seconds would be the deciseconds. This is centiseconds, so we actually have 2 centiseconds, but if we put a 0 after it, we have 20 milliseconds, because milliseconds is in the thousandths place. There's a couple of ways we could actually create the PWM, and that's in code. We could say, let's wait for, let's say we wanted to do 1 millisecond for a 20 millisecond period. So in our program, we could say, okay, wait for 19 milliseconds, and then at the 19th millisecond, we put a logical 1 to the pin that we want to put output, and we'll do that for 1 millisecond, and then bring it back down. This is a little bit inaccurate because in our programming, we're gonna have lines of programming which take cycles, and this could affect the timing of these periods. And we want these periods to be constant and always on par with the next one. So each period should be exactly the same, and then we should have the pulses pretty much the same. And if we did it this way, we would have to have too much arithmetic in the program. We'd always have to subtract what we want here and produce what we want here. Subtract this part here from this point, and then wait for that amount of time, and then do this. And we wouldn't be able to have any code in the middle of all of this waiting. So it's best to use interrupts, and we're going to be using timers for this. So if we wanted to actually create a pulse width using this timer, you can see that, let's say this is at timing 0, and this is at 128. Mr. Timer got to 128 right here, and then Mr. Timer got to 255. And if we wanted 2.5 volts, then we would tell Mr. Timer to give me a logical 1 on a pin at this point. So you're going to have this go to 0, and then at this point it'll jump to a logical 1, which is, let's say this is at 5. Let's do this, and let's not use the same scale here. Let's draw the pulse width here. So the period would be in the same location, and let's say this is 0 volts, this is 5 volts. So at this point, when the timer got to 128, it would jump up to 5 volts, and then it would come over, and then it would go back down to 0 volts. So you have the pulse width going from the center of this period all the way across. So now you have 2.5 volts if you continued this. Now if you wanted the next period to be a little bit of a smaller pulse, let's say we wanted the pulse to happen at 200, then the pulse width would look something like this. It would continue going from 0 volts and keep going until the counter got to 200, because it's counting from 1, it's counting 1, 2, 3, 4, 5, 6, 7, all the way to 200, and then it will jump to 5 volts at that point, go over, and then jump back down. So just by modifying the number at which the timer will produce a signal of 5 volts is where you're going to have your pulse. That's really simple. When the timer gets to whatever number you want, you can have this pulse outputting to any pin that you would like. We will look at this option in great detail when we're trying to control more than 4 servos. We can have as many servos as we want as we have outputs on the microcontroller. For the next tutorial with the servos, we'll be using the output compare pin, and we'll be using the internal function of PWM. So we're going to set a particular variable, or the output compare register, to this number that we want it to produce the PWM. With the 8-bit timers, we can either have a maximum of 255, or we can set the maximum to be the value in the OCR register. And this is in CTC mode, which is clear on timer compare. So let's say our OCR value is 128. When it gets to 128, the timer, it'll reset back to 0, and then it'll do that again. Go back up to 128, reset back to 0. 128, reset back to 0. We can probably achieve a 50 hertz or a 20 millisecond period doing this with prescalers, but then we wouldn't be able to use our OCR as a way to create our pulses. So we would need to do this more of a manual approach, and we'll get into more detail in another video on this. For the servo, we'll be using the 16-bit timer, which we have on a 16-bit timer. This is time again, and this is count, and we have a top value of, in 16 bits, 65,535. So we have the capability of counting all the way up to 65,000 and then dropping back down, or we can set the top of this counting in the ICR register, and then it will go back down. ICR. And then we can set another register for when it creates a pulse. So let's say this is our period, and let's say our pulse, we set ICR to let's say 50,000, and then we set our OCR to 25,000. That way, in our period, we'll start off at 0. Then at the 25,000 mark, it goes up to 5 volts, travels to where this hits, the ICR hits the top value, then it comes back down. And it does that all over again. And this is a little bit more versatile because we can get much better resolution for our servo or whatever we're trying to control. And we can hit our period perfectly with 50 hertz or 20 milliseconds. And we can set that in only 2 registers, the ICR register and the OCR register, after we set up the timing control parameters. We can also take advantage of a manual approach to doing the pulses on any pin from the microcontroller using the timers, but we'll leave that also to another video. So how does phase correct PWM work with microcontrollers and timers? I'll draw the time. This is time on this part of the graph, and this is counting on this part of the graph. And this will be from 0 to 255 again. And in phase correct, the counting through time goes something like this. It goes all the way to 255, and then it counts down from 255 to 0. It doesn't go straight down. It actually creates another angle like this. And you determine where on this line you're going to create the pulse. So if we're starting here with the period, this would be the period between these 2 marks, and you'd be at 0. And let's say we select this point to be where we want the pulse to start. It would also happen at this point because it's the same number. And this would be the OCR number. So when it gets to this point, there will be a pulse. It will go across until it hits this again, and then it will come back down and go across. So you can see that the pulse is happening directly in the middle of the period of time, the period that we're using for our PWM. We can do this with the 16-bit as well, where the top value would be 65,535 or whatever you set in the ICR register. When we do program for the servo, you will see using the timer and just applying a couple numbers, ICR number and then the OCR number, and doing some control, how effortless it is to create control for a servo with a microcontroller. So in this video you've learned about PWM, pulse width modulation, and what it takes to create the pulse width modulation using the timer. In our next video we're going to actually program for the servo to be controlled using the 16-bit timer and the PWM. And we'll do it with the fast PWM, which is assigning a top value to ICR, and then it goes back down to 0. We can also do it with phase correct. Thank you for watching. If you are following along with these experiments or producing successful projects on your own, helped by these tutorials, please let me know using the Contact Us page on the newbiehack.com website. I would like to feature these on the website to benefit and motivate others to join this creative field. Thank you.